And good morning, everyone. We'll be starting class in 1 to 2 minutes time. Good morning, everyone. And today's lecture is going to be on the topic of IIR, or Infinite Impulse Response Filter Design. But here we're going to see the two techniques that we will be using to design these IIR filters, which are known as the impulse invariant design technique and the bilinear transform technique. But in today's lecture, we're only going to be focusing on the use of the impulse invariant design technique. And then for tomorrow's lecture, we'll show the bilinear transform technique and then some worked examples of past paper questions involving these two techniques and how you will go about solving these problems in particular. Right, so let's get started with the material for today's lecture. So typically, once you're doing any sort of digital filter design, we need some analog filter prototype equation to start with. So in using the analog filter prototype design and going towards our digital design, that means the analog filters will be represented in the Laplace domain, whereas our digital filters will be represented in the Z domain. And we know the relationship between Z and S at this point in time, which was detailed in lectures 11 and given by this equation here, where Z is equal to e to the power st. So in doing the design for the impulse invariant response filters, or the IIR filters, we usually start with some analog filter in the Laplace domain, and we do this substitution here for S to change it into terms of Z in order to get the equivalent digital filter design in terms of Z, like I just said. So we're going to be exploring how do we do this in this lecture in particular. Now, IIR digital filters are used when you don't really have an importance behind the phase itself, because in doing this approximation from the analog domain into the digital domain, the phase is going to change drastically as a result. So we begin with some analog prototype in general, and we convert this by doing analog to digital mapping, and we can do this by doing spectral transformation to get the desired frequency response. And in particular, once we're doing this, we need to make sure that we don't have the aliasing effect in doing this transformation. But we need to make sure that the sampling frequency is, the frequency of the filter is going to be twice of that of the original signal frequency that we intend to filter itself. In practice, we typically use 4 times or more than 4 times this bandwidth in order to get some really good results in particular. The design approach is to choose some analog prototype, so it could be a Bollywood filter, Chebyshev, Bessel, or any other analog prototype filter that you can get. And then you can approximate the behavior into the digital domain by using one of 2 techniques. So you can match the time response, which is basically you do response invariant mapping, and this technique is known as the impulse invariant design. Or you can match the frequency response, which is known as the bilinear transform. So for today's lecture, we'll be focusing on the impulse invariant design technique, and in Wednesday's lecture, we'll focus on the bilinear transform technique. So we basically need to match this digital filter response to the analog prototype response for any given signal input. And then typically, because the inputs here deal with impulses, we just leave the inputs as an impulse. And we do record the significance of the impulse response because an impulse contains all frequencies, basically giving us the frequency response of the entire filter. In general, the transfer function obtained is typically a good match for that signal, but we're going to see what happens when we do this transformation from the analog domain to the digital domain, because remember, in moving from analog to digital, there's approximations that are taken into consideration, and this does affect the behavior of the filter itself. For other inputs, doing this design technique in particular may not match the filter itself. So this technique is only really good for impulses at the input. So for example, if we use the step or a ramp, we wouldn't get that nice close matching to what the digital domain will be matching to the analog domain. And this is particularly true for this design technique. So typically, we'll start with our x of t signal here, which is our input signal. We sample this and make this into x of n. Then we transform this straight into x of z. Now, the method that we're going to be using in particular is that we're going to have an x of t signal here, or x of t system, and we transfer this into x of s. And then, alright, so this would be our input signal. We transfer this into x of s. We know we have a system here, which is h of s, so we get the desired output signal y of s by multiplying the 2. H of s is basically our filter in this case. We then transform this back into y of t because we now have the desired output signal. We sample y of t to get it into y of n, and we obtain our y of z here in particular. Now, because we have the x of z here and the y of z here, we can formulate these two into h of z to give us our equivalent digital filter design for h of s. So this is the method that we're basically going to use for doing the impulse invariant design technique, and we're going to see this step by step. So we're going to start with some analog filter prototype design here given by the h of s equation. And we need to convert this into h of z using that impulse invariant design technique. And we're going to be given a sampling time here of 1 second, which is going to play an important role while we're going to be solving for this. So the first step is we need to figure out what's going to be x of s here. Now, because it's the impulse invariant design technique, x of t is just going to be delta of t, and if we check our Laplace transform tables, x of s here for that delta of t, which is basically delta of s, is just going to be equal to 1. Y of s is basically x of s by h of s. X of s we know is 1. H of s was given by the filter equation here, 1 divided by s plus 1. So y of s is just going to be equal to 1 divided by s plus 1. y of t here, when we transfer this back across into the analog time domain using our Laplace transform tables, is going to be y of t is equal to e to the negative t u of t. When we sample y of t into y of n, that means every instance where we had minus t or t, this now becomes minus nt of s and u nt of s accordingly. We know that we were given the value of t of s here being 1. So now that we have this in terms of y of n, and we know t of s was 1, so we can just get this in terms of n, we can transform y of n here into y of z using the z transform tables. So we can get the equivalent y of z equation here. Now in this particular case, I kept the t of s here because the t of s is not going to be affected by the transformations whatsoever. So then we could substitute in this t of s value afterwards and resolve the entire equation into numerical form. X of z was just going to be 1, because remember, in the time domain, it was just basically an impulse. So the Laplace transform and the z transform by impulse in the time domain is just going to be 1. So h of z being y of z divided by x of z is just going to be that same y of z here, because x of z was just 1. So typically, once we have the h of z equation here, this basically brings us to the end of our question. What I'm showing you here is basically what happens when we do the approximation effect from the analog domain to the digital domain by observing the spectrum of the filters. So if we need to plot this, we need to transform this from h of z into h of omega, and we saw that in last week's lecture, how we went about doing the substitution to do this. And then we plot accordingly for omega versus h of omega. And we basically see here that the phase response here for our analog filter prototype, being h of s here, the phase response here is linear in nature, whereas the frequency response is nonlinear as expected. And this is for the analog filter design, h of s. However, when we move to h of z, we can see here that the phase response here is no longer linear, it becomes non-linear. Whereas the frequency response basically remains the same here, this frequency response being the magnitude response of the filter. And in noting the phase nonlinearity here, in moving from the analog domain into the digital domain using the impulse invariant design technique, this is the approximation error that is going to occur. This is why, at the start of the lecture, the disclaimer for the impulse invariant design technique is basically you use this when the phase is not important for your application. You're only going to be concerned with the magnitude response of the filter in particular. So this approximation error occurs because of all the steps that we just now took to move from the analog domain into the digital domain for designing our IIR filter here. So that was a simple h of s equation that we just now did, but when you do encounter more complex h of s equations, it comes like if you're doing the same thing like you're trying to solve for h of t only. So you won't have to use some partial fractions to go about solving from h of s back into h of t and so forth. And your design is basically stable once you can prove that the analog prototype is stable, meaning that all the poles on the S domain are going to be on the left hand side of the S plane, being the imaginary versus real axes, whereas in the Z plane, that means all the poles lie within the unit circle, and we saw that in a few lectures back a couple weeks ago when we were discussing the Z transform in particular. And most importantly, remember the sampler frequency and the filter bandwidth needs to be twice that of the original single frequency that you're going to be dealing with in order to avoid the aliasing effect. Otherwise, the filter will not work as expected. And doing this approximation too, you want to have some amplitude scaling for the magnitude response, and it's just basically going to be a constant multiplication factor throughout the entire thing. So once you know what the original signal magnitude is, you can just rescale it back to get to your original amplitudes as required. So we can see here that our original magnitude response given by this blue line here was from the h of s equation when we were dealing with the analog filter design. And the scale version given by the green line here, it has the same shape, but we see here that we have a difference in magnitude. So even though it's the same shape here, that means it's a constant multiplication factor throughout, so we just scale that accordingly to get it back to the original part. Now, if we're given this h of z equation here, and we are asked to find the input-output difference equation, it's very simple to do this because h of z here was y of z divided by x of z, and then we can transform this accordingly using the open form solutions as required. We saw that in our z transform lectures, how to go about getting the open form solution. Once we have this in terms of y of n and x of n, and we see here that we have a delay for y of n, it's possible for us to draw a block diagram to represent this. So the generic block diagram representation here would be where we have the x of n's on the inputs and the y of n's on the outputs. And then for each horizontal level, it represents the delay level. So this one will be at n, this one here will be at n minus 1, and so forth. And we can just redraw the block diagram to suit only either in terms of z or in terms of n as required. Now, when you're designing IIR digital filters, in comparison to the FIR digital filter, we saw that the FIR filter design in last week, it was just basically a feed-forward path where there was no feedback involved. However, when you're doing the IIR digital filter design, there's going to be feed-forward and feedback paths due to the recursiveness and using pass inputs and pass outputs. And you can either use the the canonical representation if you're required to draw the block diagram, or you can use cascade and parallel realizations if it's possible for you to multiply the systems together or have them adding together and so forth in particular. Right. So we're going to use a slightly more advanced equation here for analog filter. And we're going to be doing the same impulse invariant design, and with the sampling time here being 0.5 seconds. And we're going to basically do the same steps that we just now saw in a few slides back. So the first thing that we'll do here is that we know that h of s needs to go back to h of t as our first step. So we need to make sure that in having our h of s equation here, we separate this out into partial fractions and we solve for the numerical coefficient. And then we're able to transfer this back into h of t, and then we can move this back into h of nt because we have t of s here. And then moving from h of nt, we can move back s into h of z. So I'm just going to write out the steps here because it's not on the slide. So this here will go back to h of t, and then it goes to h of nt, and t here is equal to t of s, which is seconds. And then we transform this here into h of z accordingly. Once we have h of z, and I mean in this particular case we kept the t of s here just to substitute in, so we could get this into its numerical representations without the exponential factors. We can get h of z here equal to the required equation as such. In this particular case, move from negative powers of z to positive powers of z, and then we can just substitute in our t of s here using negative powers of z or positive powers of z as required. And it's possible for us to express this h of z here into standard form by just multiplying out and then getting this into one form of equation here in particular. So we can substitute t of s here, get our exponential factors resolved into numerical factors here, and then multiply this out accordingly. And once we do the multiplications, we can then divide this out and get this back into standard form. Now, In doing this, this means that when we do multiply this out, the constant term on the denominator here is going to be some value other than 1. And once you have that value other than 1 for the constant term, and you have the equation arrayed as of such for the standard form, that constant value, you want to use that, and you want to divide the numerator and the denominator by that constant value to get this into standard form. So in order to move from this form here into the standard form, after you multiply this out and you arrange numerators and denominators into descending powers of z, so be z to 0, z to -1, z to -2, and so forth, this constant term here on the denominator, whatever you have, is what you're going to be dividing the numerator and denominator by in order to get it back in standard form. And once you do that division here, you'll get the standard form equation as required by this blue block. We'll do a practical example of this in Wednesday's lecture once we move on to the IIR filter design examples in particular. Right, and if we do our magnitude and phase responses here in particular, we can see that the magnitude response is nice in particular, but the phase response here, due to the approximation, is non-linear as required because of the impulse invariant design technique. If we compare this to the impulse response of the analog filter to the digital filter, we see here that the impulse responses do have a very close match as required due to the impulse invariant design technique. And this here is just basically the generic block diagram we can use to represent that h of z equation as required, canonical representation. All right. So that basically brings us to the end of today's lecture. And what we basically saw was the design technique used for the impulse invariant design, where we're designing for IIR filters in particular. And this was basically to match the time response of the filter itself. In Wednesday's lecture, we're going to be watching how do we match the frequency response of the filter using the bilinear transform technique. And we're going to see how this technique differs in particular. In doing the IIR filter design, we basically started with some analog filter prototype, and then we transformed this back into h of t, being the analog time domain representation. We then moved from h of t into h of nt, being our sample version of h of t, being the discrete version. And once we have h of nt, we know that t there, being capital T, is going to be a sampling time, which is given to us in our question. So we need to substitute that sampling time into that so that we get this in terms of h of n. And once we have h of n, we can use the z transform tables to move into h of z. Once we have it in terms of h of z, basically the question basically finishes there because we now have our filter equation. But if we're asked to represent the equation in standard form, we need to multiply that out and then arrange the numerator and denominator into descending powers of z. And then we take the first term on the denominator, being the constant term, I'm going to divide the numerator and denominator by that constant term throughout in order to get this into the standard form required for h of z. Finally, if you are required to do block diagram representations of these filters, the typical form that you will use will be the canonical representation, and the lectures for the z transfer function realization, which was probably lecture 13 or 14, you're going to have to use that as a reference as to how we go about drawing the canonical representation of each one in particular. All right. So are there any particular questions regarding the material of this lecture? Alright, it doesn't seem like we have any particular questions and so forth, so if there are any questions afterwards, feel free to leave them down in the comments below, or you can directly email me and ask any particular questions regarding the impulse invariant design technique that was shown in today's lecture. On Wednesday, we're basically going to be doing the second impulse invariant response, sorry, the infinite impulse response filter design that we're going to be doing, and we're going to be showcasing the bilinear transform technique, which basically was where we match the frequency response of the analog filter instead. And then we'll move on to IIR filter design examples to basically highlight the type of past paper questions that you can expect in particular for your final exam and how to go about solving them in particular. Also, we're also going to be doing problem set 3 on Wednesday once we finish with those lectures in particular. And don't forget that there's a poll online on my learning that you guys need to vote for the 3 questions that gave you guys the most trouble, or the ones that you wish for me to do live on Wednesday's session regarding problem set 3 itself. Right. One thing to note in particular is that once we finish the IIR filter design lectures, there's only going to be one more lecture that we need to cover, which is basically the special topic for DSP here. And in this particular case, the special topic is going to be the audio fingerprinting lecture as of such. You will see on my learning that there's going to be 3 lectures that are posted up. There will be DSP examples 1, DSP examples 2, and then the audio fingerprinting lecture. But we won't be doing the examples. Those are just for your information and stuff for you to read up on if you wish. The core material that we're going to be doing is the audio fingerprinting lecture, and that's going to be dealt with next week Monday, and that's also going to be our last lecture for this semester. So any other lectures afterwards, it's going to be at your request if you need to do any particular past papers or whatnot and so forth. But you're free to email me or post on the forum if you have any particular past paper questions that you're attempting and need some help with. Once I'm around, I will respond to you guys and give you a nice indication on how to go about doing the problems and so forth. All right. So until Wednesday, take care, be safe, and I will see you guys soon. Later.